I'd be happy to watch, see if I get any new emails from you. And if you want Zoom for later in the week, just tell me. I'll do this with Zoom instead, and then you can just interact with me directly. But I don't even know if you're watching this, so I feel like I'm talking to myself. And you wonder, why do people seem like they're going nuts around here? They are. Reminds me of when we were in San Francisco. When Joan and I first met, you were young, not much older than you. And we decided we were going to probably take a year off of college together. And what we did is we hitchhiked from Colorado to San Francisco. And we were going to stay with my brother and then turn around and go back into the mountains and ski somewhere for a year, take off a year of college, work at a ski area, all that jazz. If we still got along. And if we didn't get along, the agreement was that I would politely put her on a jet and she'd fly home to Hawaii. So we got to San Francisco and we were still getting along. And needless to say, we still are. And we were at Union Square, which is like the busiest center of San Francisco by far. It's a crazy, crazy busy place. And we were there one day during rush hour at the end of the workday. All these workers are, they're milling around, and this is a place where the biggest public transit system, the underground train that goes over to Oakland, it goes underneath the San Francisco Bay and everything. This is like the biggest hub of that Union Square. All the public transportation, there's just thousands upon thousands, an unbelievable number of people. And you got all this stuff going on, big city stuff, and you get, unusual people. I remember this one guy standing up on a box that he had, and he's preaching from the Bible, and nobody's listening to him, and it's like he had 1,000 people listening to him with the energy he's putting into it. And all of these other things, just crazy, crazy city going on. And then this lady comes by and she's got a doll. And she obviously had some problems going on, but she's got this doll. And she's talking to the doll, and she's treating it like it's her baby, and she's homeless probably, and she's talking to it, and we're just like, it was like real. It was as real could be. Her interaction with this doll, and most people are just like in the big city, they're not paying attention to anything but where they're going, what they're doing. And Joan and I, being young, impressionable people, were just like, oh my God! And she figures out that we're paying attention to her. And she stops and she looks us square in the eye and says, "You must think I'm going crazy or something, huh?" Like she was just acting, and maybe she was, who knows? And then she looked us even deeper in the eye and she laughs and she says, "I am!" and laughed and walked away. We were just like, ah! Yeah, welcome to the big city. It was something. So, yeah, I may be talking to myself, but I'm not saying, huh? So, complex numbers. The definition of a complex number is a number which, I've said this before, but we're going to say it again. This is the definition. It is written in A plus BI form, where A is a real value, B is a real coefficient of I, not equal to 0 typically. So, if we just wrote the number 14, that'd be plus 0i. But if we wrote, for example, the square root of negative 14, then what you're going to have with that is you've got to take an I out front, and then that ends up being I times the square root of 14. So what this is, in A plus BI form, is that because B and I are multiplied together, the square root of 14 is the B value. And then A just happens to be 0, because there's not a real component that gets added to this. So if I wrote that in A plus BI, it'd be 0 plus root 14 times I. So you're going to see in books and things like that, you're going to see imaginary numbers and complex numbers written like this. You're going to see them with the I after. I will oftentimes write them like this, so there's not any mistaking where I belongs. Although we generally do not put I underneath like-hand symbol. Because the square root of I would be like the square root of negative 1, which would be the fourth root of negative 1. And we don't need to worry about that just yet. So this is the idea of what the definition would entail. So what this lesson is about is basically working with complex numbers and adding them together and multiplying them, dividing them, and being able then to see a little bit of where they get used in physics. And physics is where they primarily get used. So if we just look at this activity a little bit, can you do some of these with me? Can you write some of these? Logan, you're there? 2 plus 3i plus 6 plus 9i. Can you do these? 4 minus 3i. Quantity added to the quantity 7 plus 5i. And then I want to jump down to a couple of the subtraction ones because those are critical, that we observe the negative being outside of a quantity. That's real important. So what if we work that first one together? Can we just add the 2 and the 6 together? And the 3i and the 9i? Think of order of operations. Can we do that? This is this plus this, plus this plus this. Yeah, we can. We can just add that together. This is like order of operations. They are in parentheses, but it's all addition. Yeah. So we can end up with 8 plus 12i. That's legal. See, if we look at the top of page 428, if you got your book open, you can save a little bit of writing here. It says addition and multiplication are commutative and associative, so we can use the properties. Multiplication distributes over addition and subtraction so that it works the same way. If you had a number outside of the parentheses, it distributes. And then 0 is equal to 0i, which is equal to 0 plus 0i. That's the additive identity. And 1 is equal to 1 plus 0i. That's the multiplicative identity. So in other words, if we add 0 or we add 0i, we're not changing the value. If we multiply by 1 or 1 plus 0i, we're not changing the value. So through multiplication or addition, that's how that works. And then there's also, every complex number has an additive inverse, which is negative I plus negative bi, which means that there's a number which is its opposite that we can add to it and make 0. So for example, any one of these with subtraction, if it was subtracting the original amount, that would equal 0. So there's really no tricks with it so far. The addition and multiplication properties of equality do hold. Oh, back up to number 4. There's a multiplicative inverse as long as a plus bi is not equal to 0, so we can have a reciprocal that you can use to multiply and get 1. So any one of these, like if you had a plus bi, and then you multiplied it by its reciprocal, this would cancel out and we'd equal 1. So all the properties are holding. So if I add these two together, you have a 4 and a 7, that's going to make how much? 11. And then I have a negative 3i. Don't forget to watch your negatives. And a positive 5i, so that becomes 2i. Then down here, we have 4, but we're subtracting. So in this case here, it's best to maybe think of this as the addition of each of these opposites. I would do that. So then you have a 4 and a negative 6, which is, and then you have a negative 3 and a negative 5 is a negative 8i. And then here, again, take this as the addition of a negative and change everything inside of here. So you have 8 and negative 1. You have a negative 4 and a positive. Oops. Plus a negative 3i. Or you could write that 7 minus 3i. Okay. So let's just look at example number 1 on the top of page 429. You see there they have 4i times 8 plus 5i, and they're asking you to write it in a plus bi form. Essentially what they're doing is just asking you to remove the parentheses, and we remove them with the distributive property. So that would look pretty straightforward. We're taking the 4 times each of the terms. So you take the 4 times the 8. Oh, I'm sorry, it's 4i. 4i times the 8, so that's 32i. And then you have 4i times the 5i. Sure, maybe we could run this one through. Is that second term 5? Yeah. The trick in here is when you take the 4i times the 5i, you've got an I squared. So we start out with 32i. And then we have 20i squared, and this becomes a negative 20, because this is 20 multiplied by negative 1. So then you have a negative 20 plus 32i. So you just have to change the order that you write them in. And that's the thing to watch for. When we take I times I, we get this I squared, which is negative. And then the coefficients, when they get multiplied together, become their opposite. So that brings into play something called the complex conjugate. A complex conjugate is, every complex number has a complex conjugate. And when we start using these numbers and we learn how to use negative square roots in the quadratic formula. So like your b squared minus 4ac is a negative number. What you get is you get complex conjugates for answers. What a complex conjugate is every complex number has a conjugate, and that is this, a minus bi, where when you multiply these together, you get a squared plus b squared. So here's what we do. We take a plus bi, and we multiply it by a plus bi. I'm sorry, a minus bi. If we take a times a, that's a squared. If you take b times bi times a, you get a bi. And if you take a times a negative bi, you have a negative abi. So those two cancel each other out. And then you have the last term times the last term. So this ends up being a negative, because it's a positive times a negative. And it's b squared I squared. But since I squared is negative 1, that ends up being a negative b squared, and subtracting a negative b squared is like adding. So this is the product of a complex conjugate. Let's see, we have 2. Yeah, let's do 2. We should take the time to do these. Let's look and see what happens. If you don't write them down, that's okay. You just want to follow along, whatever works for you. So we have 6 minus 2i times 4 plus 3i. So this is going to be an example, as you can see, of where when you take the second term times the second term, you have an I squared involved. So kind of an exercise in looking at the four products and then combining like terms. So we begin with 6 times 4, which is, and then I want to change that to a negative 2i so I don't get mixed up. And then I'm going to take negative 2 times 3, which is negative 6, but then we have I squared. And you can see that's going to turn into a positive, isn't it? When we take a look at the negative 6 times the negative 1. Okay, then we're going to take 6 times 3, which is 18i. And then we're going to take a negative 2 times 4, which is a negative 8i. So here we have like terms. 18 plus a negative 8 is 10i. And then this is going to become a negative 6 times a negative 1, so that's going to become a positive 6. And then there's 24. So we can bring these two together. We have 30 plus 10i. That's as far as we're going to take that one. So the last problem here, that's just numbers, is a division problem. Example 3. And this is going to be 3 plus 6i over 3 minus 2i. And when we simplify, what we want for an end result is we want to have I not in the denominator. So kind of like with square roots, we would rationalize the denominator by multiplying by the square root to get rid of that square root in the denominator when we're simplifying. Here we've got to do something to this to make it so that I is not present in the denominator. We can't just go and say 3 divided by 3 and 6 divided by 2. That's totally not legal. We ought to be beyond that now. These are two terms that act like one. So if we cannot take this and divide it by 3 minus 2i, and we can't, then we have to multiply the denominator by something to get rid of the imaginary component. By itself doesn't do it. By its complex conjugate. This is the trick. If we multiply this by 3 plus 2i, we are going to get a squared plus b squared. We're going to get 9 plus 4. We're going to get 13. When you take a plus bi times a minus bi, the end result is a squared plus b squared. This is a, this is b. 9 plus 4 is 13. Let's do it. What's 3 times 3? And then we're going to do negative 2 times positive 2. Negative 4. I times I squared. You with me so far? Okay, 3 times 2, 6, then I. Negative 2 times 3 is a negative 6i. These two cancel. I squared is negative 1. Negative 1 times 4. That's your denominator.
That's handy.
Yeah, it's dang handy. But then we have to do the same to the top, or else it's not going to be an equal fraction, or an equal fraction. So the top is going to look different. So here's what we got. This is kind of a messy mess, but you see what we're doing, right? We got 3 times 3. We've got 6 times 2 and I squared, which is...
Wait, 3 times 3 is 9.
Yeah, sure, why not, huh? Thanks. 6 times 2 times I squared. And then 3 times 2i 6i times 3. So there's your numerator. So let's just write it down here nice and clean. Combining like terms, the 12 times the I squared is going to turn into how much? Negative 12. So negative 12 and 9 is negative 3. I squared.
Why didn't we multiply the top by 3 plus 2i?
Because 3 plus 2i over 3 plus 2i, this is equal to 1. And we're just rewriting the fraction so that it's not an a plus bi denominator. It's just a real number denominator. So back to this. So we got this gives us a negative 3, and then that's 24i. So there, that's your final answer for number 3. Yeah, complex numbers are kind of cool. I mean, they are cool. They're fun to work with. So, applications. Physics, electricity. Complex numbers are involved in electricity. Do you guys understand anything about electricity? Did you do that in physical science at all? Okay, so none of you would have been in physics last year, but you had physical science. Or no, you had biology. You're in physical science now? No. Did you do anything with electricity? You talk about ohms? And ohms are? Yeah, it's a measurement of how much current gets slowed down. So when we have all of this electricity in these big wires and it has to go into smaller devices that don't use all of that energy in order to make that second-hand move, for example, although it's coming out of a battery. But we don't need the entire load of energy to be able to fire some of these lamps and lights and things. So what we do is we slow down the electricity and we limit how much flows into a device. And that's called resistance. Resistance is measured in ohms.
If you let all of the electricity and the light would burst.
Yeah, the device would have to be able to handle all of that electricity. And some devices can handle a lot of electricity, but not all of them need it because, we're not going to need the same amount of electricity going into that fluorescent light fixture as we do going into like a motor that's running a big fan for the heating system for the school or something like that. So impedance is how much we slow down or reduce the electrical flow, and that's measured in ohms. And they give us some information here, and they talk about it. They say, there's a nice narrative here. He says the first use of the term complex number is generally credited to Carl Friedrich Gauss. Gauss did a lot with math. So Gauss applied complex numbers to the study of electricity, and then they ended up using all of that knowledge in something called dynamic systems. So it says electrical impedance Z is defined as a complex number involving V, voltage, and I, which is current. So a complex number representing impedance is in the form of Z equals voltage plus impedance times I. So a total impedance, Z sub T, of a circuit made from two connected circuits is a function of the impedances Z sub 1 plus Z sub 2. So whether you have things in series or you have them in parallel, you end up using the math a little bit differently. In series means, for example, you have an electrical circuit where the electricity flows through a device, is impeded, is slowed down, and then that amount of electricity continues on to the next device. And then you can further slow it. If it's in parallel, you have electricity coming in and they're going towards two devices, both of them are being slowed down. So it's kind of like a river branching out or staying together, leapfrogging kind of idea. So they give us two different forms here. And in series, it's Z sub T is equal to Z sub 1 plus Z sub 2. And then if things are in parallel, it's z sub t is equal to the product of z sub 1, z sub 2 over the sum of the two different circuits. So they say find the total impedance in a parallel circuit where z sub 1 is equal to 3 plus 2i
I thought
ohms.
parallel was the second one.
Oh, yes, this is parallel, what am I saying? Yeah, because otherwise this will be just too darn easy. This is parallel, thank you. And then z sub 2 is going to be equal to 5 minus 4i ohms. So all we have to do with this problem here is plug the values in. And when we add them together, if you look forward, you're going to see that we're going to have an I value in the denominator, so we're going to have to clear that. So it ends up being a whole bunch of algebra. So first of all, we've got to write their product. In the numerator. And then we're going to write their sum in the denominator. So let's do the numerator first and finish the numerator all the way up. It's a lot easier to do that. Get it as far as we can. So we're going to take, and 3 times 5 is 2i times a negative 4i is negative 8i squared. And then if we take 3 times a negative 4 and 2i times 5, and I'll just keep going with this one. I might suggest that you work like this on your paper as well. Just keep your numerators on the same line. Don't go tumbling down. So now, can you see that negative 8i squared can be added to 15? What will that equal?
23.
23, because that makes it positive. And then these are like terms. So we have negative 2i. It's a good time to start reinvesting in writing subtraction as the addition of a negative. Good time to do that. Now we're going to add them together. So what is that going to become?
8.
Plus negative 2i. Yes. So now we have 8 plus negative 2i. And we need to multiply this by what to remove the i?
8 minus. Or 8 plus the 2i.
Yeah, it's going to be the opposite. So this is going to be times 8 plus 2i. And we have to do that top and bottom. So we multiply by the complex conjugate. So can you just see by theorem what this is?
8 squared.
8 squared
64.
plus 2 squared, because 2 is the b value. So 64 plus
4.
is 68. Okay, now upstairs we have to distribute this out, combine like terms, and then we're going to be golden. So what's 23 times 8? Do it in your head. 2 times 8 is
16.
160. 3 times 8 is
24.
160, and 24 is
4.
4. Okay, now we do these two. And we do that because when we take I times I, that's going to turn this into a real value, which can be combined with this right away. So we have a 2 times 2 is 4i squared. So this ends up being 184 plus 4, which is 188. Now we're going to take the 23 times the 2i. How much is that?
46.
46i. And then the negative 2 times the 8 times I is going to be 16i. 46i plus a negative 16i is
39.
30i. That's the impedance for can we simplify it? So this is written as 188 over 68 plus 30i over 68. Can we simplify? Yeah. Let's do the real portion. What does that become? Should we divide both of them by 2?
No.
Keep this simple. So this is, what's a half of 188?
194.
94. Okay, we can do this again, can't we? What's half of 34?
17.
What's half of 94?
49. No. 48.
47.
47. Does 17 fit into 47 evenly?
No.
No. Okay, 30 over 68 becomes 15 over 34. Can we put, no, there's nothing there, is there? So then you got 15i over 34. So we could write it like that. Or we could bump this up to a 34 and then say we've got 94 plus 15i over 34. And that's a really nice, neat way to do it. So how you get here is up to how you'd like to make your brain work. So, any questions about what you've seen so far? Okay, that's that.